In this video, I'm going to show an example of how to graph a rational function. So here we have y equals x divided by x squared plus 1. So we look at the denominator and we see that it's x squared plus 1. And there's actually no way to make the denominator equal to 0. So I'm actually going to put it in the asymptote section here. So we have x squared plus 1 equal to 0. So x squared equals negative 1. Now, I can't square root negative 1, so therefore here, there are actually no vertical asymptotes. So since there are no vertical asymptotes, and I check my numerator and see that it's just x, I can conclude that my domain is all real numbers. Now, for intercepts, when I plug in x is 0, I get y equals 0. So I have a point 0, 0. Now similarly, if I place y to be 0 and I solve for x, I still will get 0, 0. So here's my first point that I have. All right, next, let's take a look at symmetry. So when I plug in negative x into the question, I get negative x divided by negative x squared plus 1. And this simplifies to x squared, because when I square a negative, it still becomes positive, plus 1. I compare this function with my original, and I can see that they are different, so it's not even. So now I'm going to check negative f of x. So that means I'm going to place a negative in front of x, divided by x squared plus 1, and I can see that these are the same. So therefore, I have odd symmetry. Now that's going to be really useful when I graph, because then I kind of only really need to do half of the graph, because then I can reflect to get the other side. All right, so we have no vertical asymptotes, so let's check for horizontal asymptotes. So remember to check for horizontal asymptotes. We check what happens with the function as x approaches positive infinity and negative infinity. So we have x divided by x squared plus 1. And we're going to use that little trick where we're going to divide everything by the denominator. The denominator is variable with the greatest exponent, so that would be x squared. So then I have 1 divided by x. In my denominator, I have 1 plus 1 over x squared. So these two terms become 0. So I have actually left 0. All right, let's check my limit again, but this time we're going to approach negative infinity. However, because I know from before, when I divided by x squared, my numerator became 0 already, then I know that this will also be, this will also be 0. So it doesn't matter whether I am approaching positive infinity or negative infinity, I still get a limit of 0. So therefore, I can conclude that I have a horizontal asymptote where y is equal to 0. It's kind of exciting. We have odd symmetry and we have a horizontal asymptote. So it'll be interesting to see what this graph looks like. All right, so now we're going to go on to the first derivative, and then we'll take a look at the second derivative to find any interesting features. So we have y prime is equal to, now we have to use the quotient rule because we have a quotient here. So the derivative of the numerator is 1, so times x squared plus 1 minus x times the derivative of the denominator, which is 2x. All of this is divided by x squared plus 1 squared. So let's simplify. So we have x squared minus 2x squared. So we have 1 minus x squared in my denominator. So we're going to set this equal to 0. So x squared equals 1, so x equals plus or minus 1. All right, Now, we don't really need to check the denominator because we already know from looking for the asymptotes that there's no way to make the denominator equal to 0. So we actually don't get any extra critical points from the denominator. So we'll draw our sign chart. So we have -1 and +1. And we're going to put it into test points in these three regions here into our first derivative. And probably easiest is to use this one here, which is already simplified. So when we plug in, let's say -2, I actually get a negative value. Plug in 0, I am going to get a positive value. Plug in +2 into here, and I will get a negative value again. All right, so from here, I can see that I have a minimum at -1. So local min at x equals -1, and I have a local max at x equals +1. All right, now to find what these values are, remember that I need to plug in x equals to -1 and 1 back into my original question back up here. So I am going to say that y is equal to -1 divided by -1 squared plus 1. So I get -1/2. So I have a point, -1 and -1/2. Plug in +1, and I get 1/2. So my maximum point is 1.5. All right, so I have 0, 0, and then I have my minimum, and I also have a maximum point. All right, let's go on to the second derivative. So I'm going to base my second derivative on this first derivative, which I have in the green box. So second derivative, so take the derivative of the numerator, so -2x times my denominator, minus 1 minus x squared, times the denominator, so it's going to be 2, or the derivative of the denominator, so 2 times x squared plus 1 times 2x, because I need to use the chain rule, all divided by x squared plus 1 now to the power of 4. All right, lots of simplifying to do here. Now I can see that this is a little bit of a complicated numerator, but I do see that I have an x squared plus 1 here, and also an x squared plus 1 here, and I also see a 2x and a 2x. So I'm going to actually factor out the negative with the 2x, and I'm also going to factor in x squared plus 1. So when I do that from this big first term, we can say, I would have left x squared plus 1. From the second kind of big term, which is all multiplied together, I would have plus 2 and then 1 minus x squared, all divided by x squared plus 1 to the power of 4. Okay, keep simplifying. So I'm going to multiply out and reduce my numerator up here. So I have x squared plus 1 plus 2 minus 2x squared. So now I get 3 minus x squared, all over x squared plus 1 to the power of 4. All right, so when I set this equal to 0, I actually have 3 factors here. So the first factor, I can see x equals 0. The second factor, x squared plus 1, I can't find anything to make x to be 0. Sorry, to find anything where this factor will make it 0. And then the third factor, the 3 minus x squared, equals 0. X is equal to plus or minus root 3. All right, so we're going to draw our number line. Plot 0 in the middle, negative root 3, positive root 3. And we're going to plug all of these numbers into our second derivative. So we're going to choose 4 numbers this time. And when I do that, I get negative positive, negative, positive, which means concave down, concave up, concave down, and then concave up. There are there are 3 inflection points. And when I plug in f of negative, this should be negative root 3, I'm going to get negative 0.43. I plug in f of 0, and I get 0. Plug in f of positive root 3, and I get 0.43, which should make sense because it's actually has odd symmetry. All right, so these are 2 new points here. I already know the 0, 0. So let me plot everything here. So my first thing that I knew was that I have an x-intercept of 0, 0. So I'm going to plot that here. And my other piece of information is that I have a minimum at -1 and -0.5, and a max at +1 and +0.5. Okay, so I'm going to plot so 1 and +0.5, -1 and -0.5. Okay, and then my other piece of information that I now know is that I have an inflection point at negative root 3, which is about negative 1.73, negative 0.4, so it's around there. And also, that was the positive one, and then the negative one, so negative 1.73, then negative 4.3 is about, let's see here, and we have the 0, 0. And don't forget, we also have a horizontal asymptote. Okay, now horizontal asymptotes, just to talk about this a little bit, that is explaining what happens at the end. So as we approach infinity and negative infinity. So it's a little bit weird where you think, well, we have a horizontal asymptote, yet we have a point at 0, 0. So near 0, 0, it's okay for the point or the graph to go through the asymptote, but at the ends of the graph, at the negative infinity and positive infinity, it will not be crossing the asymptote. So from negative infinity to negative root 3, we have this to be concave down. So we would draw something like this. Okay, so we're going to go through our asymptote and up to negative root 3. And then from negative root 3 to 0, it's going to be now be concave up. So I'm going to exaggerate this a little bit. So it's concave up here, and then it's going to be concave down over here. And then from and this goes all the way to 0. So I should go from here, concave up all the way to 0. From 0 to root 3 is all concave down. So that would be from here to here. And then from root 3 on to infinity is now concave up. So this would look something like this.